Hydrolysis is the idea that different salts can actually change the pH. So in our picture over here, we have three different salts. Okay, the middle one is actually sodium chloride, plain old salt, and we can see that that leaves the solution green, and green was the normal pH. We have ammonium chloride, that actually makes the solution acidic, and we have sodium acetate, and that makes the solution basic. So the fact that salts can change the pH, not always, is an important idea. And it has to do with water, okay? And hydrolysis means water, and lysis means to break it up. So some of the ions in the salts actually go and break up the water. That's where that name comes from. So we want to know that salts can change pH. We want to be able to predict which way the salt will change the pH. We need to go back and explain how come that works. And then we also want to be able to calculate this effect, and we'll show that briefly. Now here we have a couple different situations. Okay, one, the top one we said was ammonium chloride. So the way to actually go back and predict what's going to happen is to look at what was the acid and the base that made up this ammonium chloride in the first place. So mentally break that up into the anion and the cation, and the positive ion, the cation, used to be part of a base. So just add an OH onto that ion. And the same way, the negative ion in your salt used to be part of an acid, so add an H onto that. So if we do that, we see that here we have a weak base, okay, ammonium hydroxide, and we have a strong acid. Now, strong acid, weak base, that's going to make the solution acidic. Now, if you see that you have a strong base, like sodium hydroxide, and putting an H on the Cl, you get strong acid. So if it's strong and strong, then it ends up being neutral. And then finally, if we say, okay, this Na is going to become from NaOH, which we know is a strong base. But if we put a hydrogen on the acetate, we get the weak acid, acetic acid. So here we get a basic solution. So acidic solution, if it comes from a strong acid and a weak base. Okay, we get a basic solution if we get a strong base and a weak acid. And if they both were strong, then we get a neutral solution. Now, if we need to go back and actually explain why this happens. Well, a strong acid is one, let's say HCl, which completely breaks up into H pluses and Cl minuses. So going back to our idea about Bronsted-Lowry, since the HCl is so good a donor at giving off H pluses, that the Cl minus is a terrible, terrible acceptor. So the Cl minus has no tendency whatsoever to grab onto the H pluses and turn back into HCl's. So Cl's in solution will just stay as Cl's in solution and not affect the pH, because to affect the pH you have to change those H pluses. So strong acids have very weak conjugate bases and will not change the pH, and that's why this solution is green. But if we take a weak acid solution, such as acetic acid, well, that only breaks up a little bit. In fact, we've calculated and decided that out of every 100 molecules, only about 1% of them break up into ions, dissociate. So there's a very good tendency for these acetate ions to go back and grab onto hydrogens and reform the acetic acid molecule. So if acetates are in a solution, in a salt solution, they will change the pH by grabbing onto these H pluses. Now we have another reaction right here to show that. So here's our acetate ion. Now this is probably a solution of sodium acetate, like we have in our cup here, or potassium acetate, just some soluble acetate salt. The acetate ions want to reform the acetic acid, so we can think of water as H plus and OH minus, and the acetate ion grabs onto that H plus and holds onto it and reforms the acetic acid. Now if it does that, that leaves hydroxides left in solution, and that's what makes the solution basic. So back over here in our cup, it turns kind of blue, and that's the basic color for universal indicator. So again, the acetate ion is what really makes the solution basic, because that is the conjugate base of the weak acid, acetic acid. So that conjugate base grabs onto an H+, it's a good acceptor, and this is where we get the name hydrolysis, because we're actually breaking up the water molecule, reforms the acid, and puts OHs in solution, which makes the solution basic. Now in a similar way, we can look at ammonium chloride. Now we were saying ammonium chloride comes from the weak base, okay, ammonium hydroxide, and the strong acid hydrochloric acid. Now ammonium hydroxide does not actually exist as a molecule. What happens is when you have ammonia in water, then there's an equilibrium, and ammonia is a good acceptor, so it accepts the hydrogen ion, becomes ammonium, and water is hydroxide. So in a solution of ammonium hydroxide, we have ammonium ions and hydroxide ions, and we also have ammonias and water. But what happens is when ammonium ions are in the solution, as we would have in ammonium chloride, the ammonium chloride is the conjugate acid of the weak base, ammonia. So here's ammonia, that's our base, and the conjugate acid for that would be ammonium. So what ammonium can do is to donate a proton and reform the NH3, but in doing so, it gives off H pluses. Now we can write this equation as I've done. Ammonium turns into a H plus and NH3. We can also include a water molecule and show that ammonium donates a proton to the water and becomes H3O plus and NH3. Both of those are good. Now we can see that in our solution we have increased the H plus ion concentration, and that's why in the cup of ammonium chloride it has turned into the acid color, because we've increased the H plus ion concentration. So again, what is actually changing the pH is not the, we said that ammonium hydroxide came from a weak base and a strong acid, but that strong acid is really nowhere around. It's the conjugate acid of the weak base that is really changing the pH. Now, what if we have kind of a slightly confusing situation here where, let's pick a different color, where we have ammonium and we have cyanide, and if I put hydroxide on the ammonium, I get the weak base ammonium hydroxide, and if I put an H plus on the CN, I get the weak acid HCN. So, we know that it's the ammonium, it's the conjugate acid of the weak base, and it's the conjugate base of the weak acid that actually change the pH. So how can we predict what's going to happen to the solution? We have to go back and look and see who is weaker. So here is our base, okay, the number for ammonium hydroxide, 1.8 times 10 to the minus 5. For the HCN, it's 10 to the minus 10. So this is a much weaker base. So we have a weak, oops, I said that wrong. Okay, this is a much weaker acid, and this is a weak base. But since this is such a weaker acid, its conjugate base will be stronger. So we're going to have a better conjugate base. This one here, the conjugate acid, is going to be weaker, so our solution's then going to be basic. So we have to look at our acid and base that originated our salt, and we find out that since it was a weaker acid, the conjugate base will be stronger, and the solution will end up being basic in this case. Now, the last thing we wanted to do was say, how can we go back and calculate the pH for these kind of situations? So this is a problem that actually has several steps to it, and I will go through this. What I'd like you to do is to kind of stop right now and see if you can solve this problem. All the information you need is on this page, and then we will go through the answer. Hopefully you've actually gone through and calculated the answer at this point, and the answer does turn out to be 8.25. And we should have that kind of that idea anyway, because here we have the salt of a strong base and a weak acid, and so that conjugate of the weak acid is going to make the solution basic. But here's how we deal with this situation. The equilibrium we really care about is the fact that fluoride is a conjugate base of the weak acid HF, and it is going to grab onto H pluses out of the water and break those up, that's hydrolysis, reform the HF, and form OH minuses. And it's the OH minus that's going to cause our reaction. It's going to cause the pH change. And so in our icebox, we are actually interested in that bottom right value, okay, the hydroxide ion concentration, from which we will figure out the pOH and then the pH. Well, we are given the Ka for HF. Now, we're interested in this equilibrium here, which is the base, the fluoride being the conjugate base. So we can set up our Kb expression. So HF times OH minus divided by the concentration of F minus. And we can calculate that with the idea here that the Kw over the Ka gives us the Kb. So remember that the constant for water is equal to the constant of an acid multiplied by the constant for its conjugate base and vice versa. So we just throw those numbers in, and here's a number that we're going to need. So that is the Kb for fluoride. Now this page is a little complicated. We start with the red. So on the red portion here, then we have filled in our icebox, our initial concentration. Because water is a liquid, we don't need to worry about any of its concentrations because it's constant. We are not put in any HF or OH minus, so it's 0 and 0. So there's our top row. And this turns into a standard icebox. So minus x plus x plus x. So 0.2 minus x, x, and x. Now, because our Kb is very, very small, 10 to the minus 11, compared to our initial concentration, then we can assume that x is really negligible. So we're going to be very upfront about that. So assume that x is much smaller than 0.2. Therefore, 0.2 minus x equals 0.2. So we go back to our K. Oops, this is Kb. It should be Kb expression, not Ka expression. We're going to substitute in x and x, all of our bottom row values. So we get x squared over 0.2 equals our Kb from the other screen, 1.61 times 10 to the minus 11. Now we just go back and solve, so you can see what we're doing is x squared equals 0.2 times 1.61 times 10 to the minus 11. We want the square root of that. And here I always take a moment to say, okay, what is my x? My x is an OH minus concentration, and that's important. So my x equals my OH minus concentration equals the square root of x squared equals the square root of 0.2 times 10, 0.2 times 1.61 times 10 to the minus 11. Now my value for x, I'm changing colors here to the blue. My value for x is 1.79 times 10 to the minus 6. I take the negative log of that, and that will be my pOH. Since this is my OH minus concentration, that value is my pOH. And I get 5.746. I subtract from 14 to get the pH. And my final answer is my pH is 8.25, which makes sense because this is the conjugate base of the weak acid HF, so I should get a pH greater than 7. So we can go back and say when we're all done, we get a pH over here in the basic range, and that makes sense. That's the end of this tutorial.